Okay. Today I will test for the first time a round. It will be a div2 round. Let's go. The authors are Olga Martynova and Anton Martynov. I personally know Olga Martynova pretty well. And she asked me to test this round. So it will be the first round that I am testing. Well, we can count a couple more. But this is the first time when I'm the tester of the round itself and not of some other event based on which there was a contest on Codeforces. Should it work? Okay, let's go. Brick wall. A brick is a strip of size 1 times k, horizontally or vertically, where k can be an arbitrary number. Brick wall of size n times m. Is such a way to place several bricks inside a rectangle that all bricks lie horizontally or vertically, do not cross the border, that each cell belongs to exactly one block. Yeah, the wall stability is the difference between the number of horizontal and the vertical blocks. What is the maximum possible stability of a wall? So we want to maximize the number of horizontal blocks. Well, can we just divide m by minimum possible divisor? By maximum possible divisor, and that is k. Well, let's think. Alright, there is some other problem. Okay, so we have a rectangle. We take minimum prime, which divides m, and we use this p as number. Actually, can't we just take minimum divisor of n? Yeah, so if this didn't work, maybe we can use minimum divisor of n. So first of all, it's easy to see that k should be prime, because otherwise it's stupid. So it doesn't divide m, so now we have to do something like this. And it also works. It's easy to see that it also works. So we just need to consider either the minimum prime in m or all primes in n. So let's go. How do we do it? We say that Actually, we have int n and int m. Okay, to do that, let's factor both numbers. Okay, then we go through this array. And what do we try? We try to take n times m divided by p dot x times, that's it. And then the same for v. What's wrong? Okay, let's do it long. Nice. And finally, yeah. Two, 7, 16. No. The difference between the number of blocks. The difference. Okay, the difference is still easily positive, so still it should be prime. But this time we have to subtract. Wait, what? The difference? I don't understand. So my answer is incorrect for 28. So when I try p equals 2, why don't I get 28 here? Oh my god. Wrong answer, test 2. Well, I knew it would happen. I knew it would happen. It's sad. What? Wrong answer, just 2? Well, what I'm doing? Oh my god, I needed to subtract. I needed to subtract the vertical blocks. Oh, this is poor. This is poor. So, okay. I needed to take n divided by p dot x times m% p dot x. Yeah, I was a bit crazy, of course. I was a bit crazy. Let's check it. Now it's 56. But here it's 64. Now I don't understand anything at all. We're trying n times ah, oh my god, okay, might be different. Okay, I didn't understand the statement 2 times. This is something bad, I believe. So actually the answer is simply n times m over 2. It's crazy that I wasn't able to understand it. But I don't think that it exactly means that the statement is written the best possible way. Inversions. We are given 2 permutations of size n. Permutation is an array of length n. Yes. You can, as many times as you want, choose 2 indices and swap AI with HA and BI with BJ. We want to minimize total number of inversions in permutations. Okay, if there are 2 elements which form an inversion in both ways. Okay, we just need to sort one of the arrays and sort the second one simultaneously. it is a known problem. So let's assume that we sorted the permutation V. So now Vi is in the ith position. So we know that in the ith position, W should be Wi. Now we return p-ans and ans. Okay. And here we return where Vi. Let's believe in my ability to sort one permutation. Problem C. You are given numbers A, B, R. Find the minimum value of XOR of A and X minus XOR B and X. Okay, this shouldn't be hard. Let's look at this thing bitwise. If we look at it bitwise, then, so if we have some bit I want to minimize it. So if it is same here and here, then in the end it will also be same. So actually in X, bits at positions where A equals B, they don't matter. So we can ignore them. Now let's look at all the other bits. So AB, and we have some place where it is 1 and it is 0. Then X simply decides where will be 1 and where will be 0. Great. So there are two cases. If there are actually many cases. So again, let's forget about all bits where x is positive, or where a and b are same. Let's look on the position where they are different. So let's assume that a is greater than b. Then we want to understand actually, does it make sense to change this bit? Sometimes yes, sometimes no. Can it be true that we don't want to change this bit? Yes, it can be. I think we just need to consider two cases. So if we change this bit, then now a will be greater than b. Smaller, no matter what we do. So after that, we want to maximize b. Minimize b and maximize a. Otherwise, we don't want to do it. So this should be quite simple now. So we read A, B, R, which are long. So first of all, if A is smaller than B, we swap A and B. Okay, if A equals B, let's just return 0. Okay, what else? So let's assume that A is greater than B. We need to find the first bit where they differ. So to do it, we need built-in citizen of A XOR B. CTZLL actually. And then we take 63 minus this number. Yeah. Okay. So there are two cases. Either we flip it or we don't flip it. Okay, if we flip it, let's at first let's try to not flip it. So let's go from I equals c minus 1. So what do we do? If A XOR B contains I, if A XOR B contains I, and R is new R is at least this power of 2. Then we subtract it. And new A and new B are XORed. Okay, and then we say that answer is maximum of answer and ups of A minus B. Then the same thing, but with flipping. No, actually, this is not what I wanted to say. So now A is at least B. We didn't flip the bit, so we try to maximize B after that. So we want A here B0 and B here B1. Great. And then here, if R is at least two to the power C, then we try the same thing. But this time we want to have it in A and not have it in B. So we want to minimize A this. Okay, so now A is at least B. So actually we want to minimize A. We want to minimize it, and in order to minimize it, we want this bit here and don't want it here. And this, in this cycle, we want it either way. Two, three, three. What's happening? We can take x equals 1. Yes, we definitely can take x equals 1. But we cannot take as well take x equals 2. Nice box. Nice box. Nice. I don't like how the statements are written. This is not good. Why is there 7? What is this 7? Ah, I understand. So the cost of the array is calculated as the maximum of the sum of blocked elements. And you just need to remove this word maximum. Sums of the segments into which the array is divided when the blocked elements are removed. Okay, why don't we just block all elements? Ah, minimum cost of the array after blocking. So it is binary search, isn't it? It's simply a binary search. Or not? No, not really, because we don't always want to take the element greedily. Ah, okay, this is some sort of window min. So what do we need? We fix some number c, which is in binary search. So we want to check if the cost is at most c. So what do we do? For each element, we want to find the minimum possible cost if we stop at this element. Minimum possible sum of these elements if all these sums are at most C, and this element is blocked. Okay, now let's consider some element. What do we need to check? So let's find maximum block such that this sum is at most C. Then we can choose any of these elements and pair them up with this one. Of course, we want to find that with the minimum DPI. So there is some queue where you can push, find minimum, and pop. How can you do it? Well, to do that, you just need to find the what? I believe it's simply a stack of suffix minima. Okay, so we have some suffix minima, which are increasing. So when we add new element, we remove all these elements until we can put A, and we put A. Then the minimum is simply this number, which sometimes is removed. Yeah, I believe that's it. Okay, let's make a structure. View with minimum. So we have this queue with minimum. So we have several functions. Void push. So we need a stack. Yeah, we need a stack. Actually, VPII minima. And I want to store the current indices. So here we say that L is 0 and R is 0. Okay, how do we push? We create a new element Rx, and which will be pushed. So minima dot emplace Rx. However, before that, we need to remove all small elements. It should be deck. So while minima dot size and minima dot back dot x is at least x, we need to minima dot pop back. Then void pop. And plus plus r. How do we pop? We say that if minima dot size and minima dot front. Actually, let's do it with while. Dot y is at most L. We say that minima dot pop front. Yeah, and then we plus plus L. Finally, find minimum. To find minimum, we simply return the front element. Okay, we have created the qmin. So what do? We initiate a binary search. So if you take the every second element, then it's easy to see okay, we don't want to take this every second element. So minimum cost can be like long, actually. So it is definitely at least 0, but it's definitely strictly less than 1e18, or even the sum of all elements. So we can write here 2e14. So while, so this is definitely a possible answer. This is definitely a possible answer. This is definitely not. While RL minus R minus L is at least 2, we do something. In the end, we return R. What do we do here? We say that M is L plus R over 2. Then we try to find this answer. So again, what am I talking about? So first of all, we add this 0 in the end. So assume that we know the answer for each element, and it's stored in the queue. Actually, we need the 2 pointers. So let's store 2 pointers, which indicate that all answers from L to R are stored in the queue. So we need int L equals 0, R equals 0. And they are stored in the queue. Now we look into all elements, each of them. I think we can add a 0 here. Okay, let's consider the element. Then the possible answer is any for which... Okay, let's assume that the sum of these elements is at most m. In this case, I just want the minimum in this queue. So I take q.findMin. Actually, I think I can push 0 initially. Yeah, I think I can. So L is -1 initially. Okay, so let's find minimum. Okay, I found the minimum. Then actually, maybe it should belong long. Yeah, it definitely should belong long. So we found the minimum in the queue, and we say that our answer is updated as maximum of QMN and our current element, which is simply it's just sum of QMN plus AI. And then I push it back into the queue. Okay, actually now I have R+1 here. Let's store our current sum. And then while Sm is greater than m, I need to subtract it. So I say that what? I say that Sm minus equals Al minus plus plus L and Q dot pop. And then if Q dot find min. Let's also store the last answer. And then if last answer is simply less than or equal than m, then it's a correct answer. And I say that r equals m, else l equals m. Not good. Ah, 8, 8, 13. No, definitely not. Okay, for example, it said that the answer 7 is impossible. Let's look at the sum answer 7. I want to look at the answer 7. Okay. So what did I do? What did I do? A, 0, 1, push, and now we have 5. And we definitely had to pop back. Ah, no, we still don't have to do it. So the answer is 5 now. Yes. Now it's 10, and it's greater than m, so we need to subtract. No, okay, so now sm is 5. Yeah, correct. Okay, we didn't have to pop back it. Okay, it seems like I didn't need to have l equals -1. It seems like I needed to have 0. Yes? Mm-hmm. Do I always work correctly with ints and longs? Of course. Not good. Not good. Why? Why do I keep doing this? This is even not funny. Maybe people who just use define int long long, they are right. I'm the only one who just solves A, B, C, D. Oh, interactive problem. So the coordinator chooses number x. Is it known in the beginning? The interactor in this problem is not adaptive. This means that actually I can use random, and using random this problem is quite easy. Using random, this problem is quite easy. So we read n. Actually, let's not do this. Let's simply t equals 1. We read n. Then we need to work. Let's remove on PC files for now. So the find answer is AVI. Ah, the number of test cases. There is a number of test cases actually. Okay. I can actually use handle here. So let's find the answer. Okay. So now we go through all the array. No, not find answer. Why? The query. So how do we make a query? We ask about I. Then we can read a character. So this is what happened with X. Let's store some number X, which is initially 0. Actually, I changed my mind. What? I don't have a solution. Don't have a solution. Oh, this is an interesting problem. I don't know. I thought that I could do it at random, but actually the expectation of the random solution is something like n squared. So let's assume that the permutation is random. It's really random. Okay, at first let's make our element x equal to the first one. I got it. It's called quick sort. So I choose element at random, then I compare everything with this element. Yeah? So assume that I have some elements here and some elements here. Then I consider these elements and these elements. Recursively. Here I again take some random element. Oh, okay. Okay. Okay, let's do it. So I take this element, x, which is initially 0. So what do I do? Actually, I still don't like it. I still don't like it. Oh no, it seems fine. It seems fine. I have the answer. So what do I always do? So we run quick sort from 0 to n, ord, and ans. How do we do it? Again, so we take the leftmost element, which we have. We find it. How do we find it? We simply take, let's also have int x. So while true, int delta equals query of ort l, x plus equals delta, and break if delta is 0. Okay, after that, we know that element ort l is simply x. So we say ans ort l is x. Then we need to do the following. We need to firstly put all elements which are less than x, and after that all elements which are greater than x. How do we do that? So what do we do? While what? While TL is less than TR, we try to do the following. So what do we do? We take this, let's take the last element. Okay, fine. We do the following. So while true, while TL less than TR, we look at the element ort TL. We ask about it. So if query is greater than 0, this means that it is greater than x. So we need to break. Else, if it is less than 0, then it's fine and we need to increase tail. Okay, after that, we found an element tail which is greater than x. We continue. Okay, at some moment, either TL equals TR, and this means that we are happy, or, so let's assume that TL is less than TR. Okay, if TL is less than TR, then we need to swap ord TL and ord TR. After that, we actually need to increase TL and decrease TR. At some moment we broke. This means that we found the division. So now we need to run this wasn't correct. So I always need to vary back. Great. So now we need to quick sort L plus 1 TL or dunce X. And then we need to quick sort TLR or dunce X. Is that it? I hope so. And answer must return a value. Okay, actually, yes, we didn't return a value. Let's find the minimum value of ans and subtract it from all elements. Not much time left. Not much time. Okay, let's think of this permutation. Let's try to do it. So I need to press 1, then 5. So they ask about 4. Fourth element. I say that it is greater. Greater equals 1. So now I have 5. I need to remember that I have 5. 1 is less. What is 0? How are you asking about 0? Actually, I need to add 1. But here I needed to write ord L, of course. Yeah, let's try again. 1, 5, again 4. Greater equals 3. 3 is less. 2 is less. 5 is less. And 1 is also less. Actually, here I needed to say that if L is at least R, then break, then return. Yes, now it should be better than before. Again, 1 and 5. 1. Okay, it's less. 1, it's equal. So now we have 2. What happened? Yes, this was a bug. 1 less 1 equal 3 less greater less greater less. So we have 2, which is greater less. Okay, now it asks about 4 for some reason. Why? I don't get it. Why 4? It already asked about 4. What's happening? Okay, fine. I guess it's fine that it asks about 4, although it didn't have to do it. Now 3. Yeah, 3 is less than equal. So now we have 1. Now it asks about 4. It will be a long journey because I will go up a lot. Up, 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 then equal. 2. Now we have 4. Less, greater. Less, equal. Fine. Fine. Wrong answer, test 8. Does it mean that we spent too many operations? Maybe yes, maybe don't know. Whatever. Okay, let's just make how it's called, interactor for this problem. So here we usually let's run some stress. What will the stress do? It will create some permutation. Okay, let's assume that it created some permutation. Then let's create a clever interactor. On this permutation. And also x is uniform in distribution from 0 to n minus 1. Okay, so we have query and report answer. And we have report answer. After that, okay, let's find the answer. So if, let's also calculate the number of queries. So if inter dot term is not inter dot reported, and if inter dot n and inter dot q is greater than 35 times n, okay, let's go. Okay, let's go. Slow. A little bit too many. Okay, it's kind of fine. We just need to work more accurately here. So here, if we know that tr is tl plus 1, we simply minus minus tr. Still slow. Okay, let's just print it. Usually it's enough, but sometimes it's greater. So we need to somehow speed it up. Okay, there is a room for speed up, and the room is actually here. So we never really need to go back each time immediately. Let's think what we do instead. Okay, we know this number, and we know x, the current x. So we compare x with current number. If it is equal, it's easy. Assume that we want it to be less than our number. If it is, so let's assume that x is less. So this is AL. Yes, so we have here we have AL, and here we have x. So if our number is here or here, then we are fine. We are happy. The problem is if our number is here. Then let's go with our number up. And the moment it reaches AL, this means that that number is actually greater. So how do we implement it? So now we are somewhere here. So first of all, I want x to be I actually kind of liked this solution, so I hated that it takes too many operations. And usually it doesn't. Moreover, if I replace it with like 1000, it should be fine. No, it's still big. It's kind of fine. Okay, let's do something about it. Maybe we need another solution? I don't know. Maybe we need. So, for each element, let's assume that initially our number is x. We know that it is between 0 and n minus 1, yeah? Yes, we know it. So, we know that each element in our permutations is from n minus 1 minus n minus 1 to n minus 1, if we think that initially x is 0. So we just need to, maybe we can do it greedily. Let's just, for our x, choose the interval which is best for it. Which divides it best. Okay, let's try it, actually. So what do we do? We have vpii v of size n, pi minus n minus 1 and n minus 1. Then we also do something. Let's say like int found equals n minus 1. Then while true, while found is less than n, we do the following. We take our x, go through all elements here, Let's go through all elements. So if vi.x equals vi.y, then continue. It doesn't interest us. Doesn't interest us. So if otherwise, let's say the following. Let's actually minimize the distance. Yeah, actually, yeah. This is what I want. So let's say that we have minimum of what? So there are two segments. One segment is x minus vi.x and vi.y minus x. And if mn is greater than biggest mean, then we take best I equals I and biggest mean equals mn. Great. Now we have chosen the biggest mean and best I, so we try okay. Then we say that int delta equals x inter dot vary of best I, then x plus equals delta. But before that, if x equals delta, if x equals delta, no, if delta equals 0, then v best I dot x equals x and v best I dot y equals x. Else if delta greater than 0, then what? Then our x is increased. This means that this is greater than x. So we say that this is max of this and x plus 1. Else it went down. This means that this number is mean of this and y minus 1. Okay. And if now found and not was found, then plus plus found. And in the end we return in the end we do the same actually. We say that we have vi ans of n. We go through all numbers. Then we find the minimum element. We subtract it and we return it. $13? What? 13 is too good. Okay, I accidentally solved this problem much better than it was before. I hope so, at least. Maybe I didn't. Yeah, Happy New Year. Oh, I don't have any time for these problems F and G. Why do people have problem with problem C? It's so easy. What's wrong with you guys? It's much easier than these two problems. Okay, I won't open them since I didn't have time and I won't solve them actually in this short limit. Okay, thank you for watching.